Yeah, welcome guys. Today I want to talk about my bachelor's thesis in physics. And as I did the bachelor's thesis in English, I will do this video also in English. My bachelor's thesis was about conserved quantities of electromagnetic knots, and in particular a special kind of electromagnetic knots, which we called de Sitter knots. Sort of the talk will be split in 3 parts. First, we're gonna talk about Maxwell equations and its symmetries, as we are trying to formulate Maxwell's equations that we know from the first year of study, and to generalize it to manifolds. And with that in mind, we can construct the electromagnetic knots on the de Sitter space, and the final part will be to talk about the calculation of the conserved quantities. So, to start off, Maxwell's equations are describing the electric and magnetic field, not usually called B and E, with the 4 Maxwell equations that we all know in this way, more or less. But in this case we're considering, sorry for that, we're considering the source free Maxwell equations, which means that rho, the charge density, and J, the current density, is 0 in this case. Just to simplify things and to be able to calculate things analytically. And to formulate these equations differential geometric, we need a space-time manifold, usually called M. And with the parameterization by coordinates, we also can define the tangent space on each point as the derivatives with respect to the coordinates and linear combinations thereof. Also the cotangent space, or the space of one forms, which is the dual space, can be formulated with using the coordinates. And for the formulation of Maxwell's equations, we also need a metric tensor, which is a scalar product on the tangent bundle, but in every point in the tangent space. The one forms are usually used to do the integrals, and what the electric and magnetic field will be in this formulation. They are together described as the field strength tensor, and we see that the components here are the electric and magnetic fields, and also we see that the field strength is antisymmetric. So we can write it out in this way with two forms. So usually we call it a two form. Because it is an antisymmetric tensor. And it's a 2-0 tensor because it's always the wedge product of two cotangent vectors. And that's why we call it a two form. It's an antisymmetric tensor of rank 2. Yeah, and it's also equivalent to defining electric and magnetic field, as we can read off electric and magnetic field if we have a time direction, and we can also define the field strength when we have coordinates, and we just insert it there. And now we can see what the geometric form of the Maxwell equations is in the setting of manifolds. And therefore we have this Hodge star, which is the Hodge dual. And it depends on the metric. And it gives, it turns a two form into a two form, and one forms into three forms, and vice versa. So it's a dual in that sense that the wedge product of those of A and star A is proportional to the metric. So it depends on the metric. And the second Maxwell equation is just the exterior derivative that you should know from differential geometry. So what we now see is that conformal maps and isometries are symmetries of Maxwell equations, or at least in vacuum, because in case of non-vacuum we have that J is just unequal 0, but in case of vacuum this is 0. So in this case for isometries and conformal maps nothing changes, and here with 2 times the star those conformal changes will cancel out, and for isometries the metric doesn't change, so it also changes nothing there. And also what we can then define to have a more general overview is the potential, and it's a one form A such that the exterior derivative of A is equals F, the field strength. And we can then therefore formulate the Maxwell equations with A, and there's also a gauge freedom, which is not usually called symmetry because it's just a redundancy in the description when using the potential, and it just boils down to that A plus the exterior derivative of some function is also sort of equivalent to using A because when taking the exterior derivative of that, then the second exterior derivative is always equal to 0. And there's also something that we can use when we have continuous symmetries, just in the case of the conformal symmetries and the asymmetries. We can describe that with a conformal group, which is a Lie group. And because we have continuous symmetries, we can use the Noether theorem to get conserved charges. And therefore it is useful to define an action functional as the integral over some Lagrangian function, because then one can do explicit calculations to find out with the symmetry of that. We can then find out a charge or current J mu, and this will satisfy, because of the Noether theorem, that it is divergence free, and the charge is conserved because when you take the time derivative of the integral over the 0 component of that would be equal to the integral over the divergence of J, K, where K are the 1, 2, 3 indices, and this is independent, and this gives 0 because we assume that the JKs will fall off to infinity. So there's also the explicit example of the translations, where we have the symmetry x is mapped to x plus a for all spacetime points, and then the conserved charge. We have 4 conserved currents in the stress energy tensor, and the parts that are the 0 components are T00, which is 1/2 E squared plus B squared. The energy density, and T0I, which is the cross product of E and B in the ith components, which is the Poynting vector, or the density thereof. And integrating that gives conserved quantities. So now we come to the explicit construction of the de Sitter knots, and the first part of the construction is that we construct a conformal equivalence of the de Sitter spacetime ds4 and Minkowski spacetime R1 3 Minkowski. And here this is not explicitly de Sitter, but it's an interval times the 3 sphere. So those are all four-dimensional manifolds, and we have the coordinates of those. Here some time component and for sphere coordinates, and here in this case we have the de Sitter coordinates, which are in R1, 4, and it is in hyperboloid, so it satisfies these equations. And here in Minkowski space we have also the XYZ components. And what I didn't mention yet is that we in the spatial components we omit that we rotate around some axis. So not around some axis, but we have we have two additional dimensions, and this is due to the fact that the when we have the radial coordinate for the three spatial components, then the angular part is equal in all three spacetimes. So we can just look at t and r, and in this case here psi and tau, and then we finally get a relation between those two set of coordinates, and one can show that it's bijective because we can write down and the two maps, and it's conformal that one can calculate explicitly. So in total we have the equivalence of the spacetimes, and with that we know that solutions in this Minkowskian Lorentzian cylinder, which is I times S3, is equal, or corresponds to solutions in the Minkowski space. We now want to go further and construct explicit solutions on this Lorentzian cylinder. And what we do with that is that we separate the dependence on the time and on the three sphere coordinates, and then we use something that makes the calculations easier, which is that we get an explicit basis of one forms, which is left and invariant. And left invariant means that we regard S3 as a group. And on the first hand you can directly see that, but this can be done by identifying with the quaternions or with a known Lie group SU2C, where we have multiplication, and therefore we can also define multiplication on S3. And this is the theory of Lie groups, we therefore know how to get how to do the translation of the basis in the tangent space of the unit. So this is tangent vector at the identity of the group, and we can just push forward it to any point in the manifold, and therefore get in a left invariant vector field. And the thing is that it also needs to be nowhere vanishing, and this is possible because we're in 3 dimensions. And what is important if we have this Lie algebra then are these coefficients, so these here, and what is also clear and can be proven formally is that this gives then the Maurer-Cartan frame, which is the dual basis to that. So in total we get a basis of 1 forms, which is nowhere vanishing and left invariant, and a basis of vector fields, which is nowhere vanishing. And we can also do that for right invariant or right multiplication. Right, and as I mentioned before, because of the map from the cylinder to Minkowski space, we know that the differential is a conformal map on the tangent space, and it's also a linear map, and therefore we can do the transformation to Minkowski space. So we know that the 1 forms EA are just related with that matrix, or with that linear form, by some matrix. So we can express it as a matrix if we expand it into the basis, and we have just proportionality here, and then we can do the transformation to Minkowski space. So we know the field strength F, or the potential A, so also the electric and magnetic field, and then we transform it over to Minkowski space. Now the explicit solution is first solving it on this Lorentzian cylinder. First we express it in the basis. So we have the basis of 1 forms, 1 for tau, 1 for the spatial part, and we simplify the equations using that. And then what is also possible, so here we have A, B, C, and summation convention. So we know from before that we have the gauge freedom, so we need some gauge conditions to get a unique solution for the components, and therefore we use the temporal gauge, which means that the time component is 0, and we use the Coulomb gauge. It's not directly the usual Coulomb gauge and temporal gauge, as we are not in the Minkowski space but on a Lorentzian cylinder. And to go on further, as we see here, we have this action of the right invariant vector fields. Or more explicitly, the components of the right invariant vector fields. And with that, we define ladder operators. So, making it all imaginary or using complex numbers. We just simplify that so that in total we have better commutation relations. And here with this epsilon, it's similar to before, but now instead of the 2 we have an I. And we also write down the new components that correspond to the I plus minus component of the potential. And now, as we always do, we have introduced now some more symmetric things, and we can now further simplify the equations from before. So these here, write it down in the new components, so for A plus, minus, and A3. And the third part is just the gauge condition, so the Coulomb gauge condition. And what is now helpful is to regard the spherical harmonics on S3. So we want eigenfunctions of the Laplacian, which is equal to j squared or also to I squared for the left and right invariant vector fields. And so this is in fact should remind everyone of a similar calculation in quantum mechanics, where we impose eigenstates or eigenfunctions of the Casimir operators, which are j squared and I squared, and commute with both the i's and j's, and also the j components and the I components are mutually commuting. And so we get like the standard j times j plus 1 for the I squared and j squared, and we get two like spin projection quantum numbers for I and j. And now with that we can also find an explicit form, doing a lot of calculations, and but that was also fun, but it's long calculations. And we remind ourselves now that we wanted to solve the equation from before, so we now want to express the potential components into the harmonics, and therefore we use a complex linear combination of those spherical harmonics. And what is cool about that is that in total we get that the j dependence is gives a harmonic tau dependence, and sort of the spatial dependence is only in the y's. Yeah, and now we have the final solution, which are the components in this cylinder. And this is a basis of solutions. So we have two types of solutions with different frequencies. These result because we have we calculate eigenvectors and eigenfrequencies. Therefore, we have two different eigenfrequencies, and we see also that we have, like, for every basis solutions, we have different spherical harmonics. And those are directly related to an index that we associate to the solution. Index. And for the other type it's different constants, but similar form. Yeah, so now what we do in a Minkowski space is that we split the field strength tensor into an electric and a magnetic field. This is the same that we do for the for the Lorentzian cylinder here. And as we know that we want to have a real electric and magnetic field, we also need a real superposition, and therefore we can insert the calculations from before using the real part. So we have number plus complex conjugate and half of it, which is the real part. This is just how we calculated it, and therefore we obtain those electric and magnetic fields, and we can also find out that the electric and magnetic field in Minkowski space are directly related to the electric and magnetic field in this cylinder. And this also means that the energy density which is E squared plus B squared, is also proportional to something with those curly E squared. So we express every conserved quantity now that we know in Minkowski space with the corresponding parts in the de Sitter space, in the cylinder. And as we can list the conformal transformations, we can first see here that we have the isometries. So first the isometries of the space, giving the energy and the Poynting vector and the angular momentum, and also the boosts. Give those as boosts are an isometry of the Minkowski space. And we also have conformal transformations. and those give special conserved quantities. Again, those are all calculated using the Noether's theorem. Yeah, and we can also write down the corresponding densities of those. Yeah. So yeah, just maybe one quick recap. So one of those transformations could be the inversion, which is also a conformal map, and the calculations of the conserved charges is just the integral over space of the, in this case, the energy density at the time t0, which in this case is, we choose to be 0 as it simplifies the calculation, and we integrate over x, y, and z. So over the spatial part. And t equal to 0 is it's important, as it also means that the tau in the cylinder is equal to 0 using the transformation. Alright, and now finally we want to calculate, so we transform the integral using the transformation law. So we have e of t x y z, and this will be equal to an integral over the space component in the cylinder, 1 over the determinant of the Jacobian, which is the matrix corresponding to the differential, so the map from the Minkowski space to the cylinder, and we have some different function now depending on those 3 sphere coordinates. Yeah, and with final computation, that I also spoiled before, we know that this is proportional to e squared plus b squared, and this can be further simplified using some properties that we can prove or show or calculate. This is 1 plus the 4th coordinate of the 3 sphere times e squared plus b squared. And as we integrate over the whole S3 in this case, we know that this part gives 0 integrals as we want to further calculate. So what can be shown in general to do that is that if we have a function of those sphere coordinates and then two spherical harmonics, and we integrate over that, having an odd degree polynomial gives 0 integral. So this is also true for f of is equal to 4. Yeah, and this is how we can calculate this part, because as we know, the expressions of this are just dependence, are just constants times those spherical harmonics, and if we square that, we get just integrals of that form with omega 4. And yeah, so in total, to conclude now, we know that we have calculated the energy for a fixed type, and so we have the dependence on these frequencies here and fixed spin J. So if we have a superposition with only one J and only one type, then we can calculate the energy of this knot, which is very cool. And also for J equal to 0, we could prove that the boost and dilation is equal to 0, and that Q, which corresponds to some conformal transformation, is also proportional to the energy. And we could calculate for the Poynting vector for the angular momentum and this V examples with J equals to 0. And what was also interesting to see kind of coupling between basis solutions, as we so we have, for example, basis E1, E2, and a linear combination, a complex one. Then if there's no coupling, that means that it's just proportional to C1 absolute value squared and C2 absolute value squared. But for coupling, it's also C1 times C2, or perhaps with a complex conjugate, depending on how you explicitly calculate. So if you want to know any further details, just ask in this group at Hanover, probably. And to conclude, for me, it was a great possibility to explore what is done currently in this working group. It was also fun to get to know the details of something and to really dig into the calculations. Here also the things that I cited in my thesis. Thank you for listening, and see you in the next video.